Hello, everybody. Welcome to session A6. Which type of SSD is best for your application? We're happy to have you join us with us. I think we've had a pretty successful event so far, and I hope that you're all enjoying yourselves. Again, my name is Brian Berg. I'm technical chair of the Flash Memory Summit, and I've been in the storage industry since the 80s. If you could back up, please. Thank you. Let's see. Yeah, next slide, please. Very good. And I'm also part of a IEEE group called the Consultants Network of Silicon Valley. We have one of the show floor booths here. So I hope you'll visit that when you have a chance in between sessions. If you go on to the next slide, please. One of our participants is Matthias Bjorling. Matthias lives in Denmark, and he's got actually a very interesting background with regard to zone namespaces that he'll be talking about during our panel today. You might have heard his talk earlier this morning in the A5 session, where he talked extensively about zone namespaces. He got his PhD at the University of Copenhagen in Denmark, and the subject of that was actually what became Open Channel and what is now transitioned into zone namespaces. So I, without any hesitation, say he is the key person in the world to talk about zone namespaces. So it's a pleasure to have Matthias with us. Thank you, Matthias, joining us from Denmark.
Thank you.
And on to our next slide, please. We also have Karam Malik. He's from Marvell. Karam is a senior technical product marketing manager there, and has worked extensively in the flash industry there at Marvell and previously at Samsung, as well as SK Hynix and Broadcom. So he brings a lot of perspective with regard to particularly Ethernet SSDs and the use of Ethernet in connection with EBOFs or Ethernet bunches of flash. We'll be talking about that during our panel. If we go on to the next slide, please. Our third participant is Moshe Twito. He's joining us from Tel Aviv, Israel. PlayOps is one of the companies. They actually joined us last year, but they're making a big splash at this year's conference as one of the keynoters, and also participation in a number of the sessions. And Moshe is the CTO of PlayOps, and he brings a perspective with regard to their new storage processor that allows connection to SSDs, particularly for databases. And there's also an interesting connection of ZNS with their architecture as well. So that will be part of our discussion today. So if you go on to the next slide, please. Great. Take it away, Matthias. You can talk through your slides now.
Awesome. Thanks, Brian. Thanks for the introduction. So namespaces, ZNS SSDs. It's a new type of SSD. I mean, it's originally came open channel to concepts, and then they became more and more popular, and then suddenly we need to standardize some of these concepts, and it became to zone namespaces. It's a rather new specification within the NVMe Express organization. Was released back in June. It's what it does is it's a new way to store, to kind of collaborate on data placement between the host and the SSD. The idea is that in a conventional SSD, when you write data onto it, the granularity of which kind of the SSD manages this data, maybe it writes it all data in from different applications into a single block, which is a gigabyte large, which means you have random data going into it, which means ultimately it's kind of a log structured approach where you need garbage collection. So on SSDs, this garbage collection is being handled within the SSD. And what ZNS does and enables is for the host to tell the SSD, go place this data into this kind of management unit within the SSD. And when doing that, you get a bunch of benefits. And what's special about ZNS is that it requires both that the SSD supports it, but also your host software needs support for it. Next slide, please. So there's three things that are what you get from ZNS. is that you improve the dollars per gigabyte. This is due to less media provisioning within the SSD. There can be less DRAM, for example. The two other parts is regarding performance. Since there's no traditional SSD garbage collection occurring within the SSD, you also get significantly higher throughput compared to conventional SSD, but you also get significantly better latency. So you get both higher throughput and lower latency. So the two graphs here below, the one to the left, what we're seeing here is where you write randomly to a drive and you fill it up once and then you fill it up twice. And the green line is the ZNS SSD, and the gray line is the conventional SSD 7% overversioning. It's the same platform, SSD platform, and the conventional SSD is a production drive, enterprise grade, and yeah, ZNS is pre-production at this point, but it's also targeted production. And what we see is that as soon as you kind of get through the first write, the garbage collection kicks in, and we see a 4x reduction in the write throughput on the conventional drive. So the ZNS SSD is doing around a gigabyte write per second, where the conventional drive does 236 megabytes per second. So a normal SSD would only be able to achieve this steady state of 230 megabytes per second, where with a ZNS SSD, you get the full bandwidth. Also, that has also an impact on the latency. So on the right side, we see the average read latency while doing write. So we are doing 4K reads, random reads. And imagine we are doing, and the maximum write throughput is 1 gigabyte per second. And imagine we write 100 megabytes per second. When we compare a conventional SSD versus the ZNS SSD and like a 90-10 random read-write workload, the average read latency improves by 29%. And it gets even better as you kind of move to an 80-20 random read-write workload, where the average latency improves up to like 57%. So not only do you get better dollars per gigabyte, you also get improved performance, which is quite unique with these type of SSDs. The con is that you need software support for it, and we have Linux, a lot of support on the Linux ecosystem, and Moishe will also talk about what they're kind of doing to also add support into the ecosystem. Thanks.
So Karam, take it away.
Okay, thanks, Brian. Today I will be talking about Ethernet SSDs. It has multiple names: fabric attached SSDs or Ethernet attached storage. So when we talk about storage, first thing comes to our mind, whether is it like a server side or is it on the storage target side. So my part of this presentation will be focused on the storage target side. And let's get started. So one more click, please. First thing, when we look at it, what's current architecture out there in the market and what industry has been adopted is a JBOF, is called just bunch of flash. One click, please. And on the very left side, this is the very high level component goes into the JBOF. And first thing, we have to decide what kind of CPU we would like to use in this architecture. That dictates whether do we need a PCI switch in between for fanning it out, and how many DDR are required based on the number of channels does it support. And also on top of it, we need to decide how many smart NICs can goes in a 2U enclosure, right? So when we think about this architecture, it's also start with all the limitation what comes with that, which comes with the CPUs, which comes with the DDR bandwidth, and which comes on the NIC connectivity perspective. And industry has been adopted NVMe drives, and the most important benefit of these NVMe drives are high bandwidth, high throughput, low latencies. And putting these drives behind this architecture challenge the bottleneck of these NVMe drives, and customers don't get the full throughput of these NVMe drives from the 2U enclosure. We always talk about moving from PCI Gen 3 to Gen 4 to Gen 5 from a single drive perspective. But the bigger challenge comes into play when we put these drives in this architecture, which has its own bottleneck from the connectivity perspective, and the amount of CPU is required to process the data, and the DDR is required to pump the data for the data movement in and out to the CPU to the smart NICs, right? The other challenge what we have seen talking to the industry is the reliability and the components, and the scalability is the highest challenge because it it adds the higher footprint means you need all these components for the connectivity perspective just to get exercise the data behind NVMe drives, and it's a highly complex and highly expensive solution in terms of cost perspective. When we talk about the amount of DDR is required, the amount of compute is required, and the number of smart NICs needed just for the connectivity, right? And if you click one more, please. And and the other question comes into play that, okay, how does this Ethernet SSDs can connect? Where does it connect? And what would be the architecture? And what are the advantages of these Ethernet SSDs? So on the very right side, what we are showing here, it's a EBOF, Ethernet bunch of flash. As you can see, this architecture replaces all the bottlenecks which we can encounter on the very left side with the Ethernet switch. So the PCI, the CPUs, the DDR, the NICs are replaced with the simple Ethernet switch. It's the L2 Ethernet switch, and on the front end, customers can use the standard Ethernet SSDs. So Marvell has a product. I can talk more about it. We are offering NVMe over Fabric Converter Controller, and we are partnered with Kioxia. They are offering the Ethernet SSDs. Those products can be used to enable the high bandwidth, high throughput, low latencies, and getting the full utilization of these NVMe SSDs and exposed to the host, right? The other challenge what we can, yeah, so better utilization, yep. And the most important thing is this architecture from a 2U enclosure, we can provide the up to 20 million IOPS from a 2U enclosure. We always talk about a single drive performance. PCI Gen 3 gives 3.5 gigabyte. Gen 4 is gonna give 8 gigabytes per second, and Gen 5 is gonna give 16 gigabytes per second. But the challenge is if we put these high performance drives into the architecture, which has its own limitation, the customers are not really getting the full advantages and the benefit of the NVMe drives, and they are paying for it to get the real advantages of using these drives, right? And this architecture can enable all the bottleneck. This Ethernet switch, it comes with 1 terabit all the way up to 12.8 terabit. It's a ASIC, it's a silicon, sits inside a 2U enclosure, and it provides the fan out to the Ethernet SSDs. And the other beauty, it does not it, this architecture does not provide the high performance. It also provide the better TCO. This architecture provides 50% better TCO compared to the JBoF architecture, which shows on the very left side. 50% is not only about high performance, high bandwidth, but also about better TCO, better costs, and better utilization of the each SSDs. The second thing what we have seen here, when we talk about scalability, how we can scale from one box to another box. This architecture is much more efficient, which provides higher scalability and higher throughput in terms of connecting one EBOF Ethernet bunch of flash to the other EBOF rather than connecting to the top of the rack. On the very left side, we have to have compute, DDR, and smart NICs sitting on the back just for NVMe drives on the front end for the connection. It's like 1-to-1 ratio. Here on the very right side, we don't need to have those components. We can have one, if we want to expand the storage expansion shelf, we can have these Ethernet SSDs connected to the Ethernet switch in an EBOF and can provide high capacity, high throughput, same time, low latencies, and better utilization. Next slide, please.
Go ahead and go on to the next, please.
Okay, so when we look at it, what is the traditional, how does the traditional storage architectures looks like? On the very left side, you can see we have a compute where our OS resides, and it's those our operating system resides and run on the compute node. On the compute connects to the Ethernet switch, and those Ethernet switch connects to the target storage nodes, and those target storage nodes provide some data protection services, and those storage nodes connects to the JBOF through either a final fiber channel, infinity band, or some other proprietary transport layers. And the adoption of, you can think about this architecture has came from back in the SaaS days when the industry was started with the SaaS SSDs, and moving one more click, please, and use the same architecture for moving to NVMe drives. Use the same architecture, converting from, but on the front end, they change the drives from SAS SSDs to NVMe SSDs. And how, one more click, please. And how we can see we are simplifying this architecture with with what we are showing here, a disaggregated storage of NVMe or Fabric target side, either could be used on a Rocky V2 transport or NVMe over TCP. So this architecture is much more simplified because it's unified the transport layer, the storage, the compute, communicate through Ethernet switch on a Rocky V2 or NVMe over TCP. And then we have NVMe over Fabric on the target side, connects to the Ethernet switch, which is sitting on the top of the rack. And one more click, please. And these PCI drives can be converted or replaced with the Ethernet SSDs with the EBOF. So these can enable the higher bandwidth and higher throughput of these drives fully exposed to the host and provide the with the low latencies application, right? But you can still see it has a lot of components in between, like you need to have the NVMe over target storage node, and how we envision moving forward, it's gonna be more simplified. One more click, please. Yeah, it's gonna be simplified completely, moving all the NVMe over target applications onto the compute and simplify, provide the JBOF for an expansion shelf. So all the compute, the storage services will be moving, providing an orchestration layer on the compute side and providing the EBOF for a storage expansion shelf for higher bandwidth, high throughput, low latencies, and better utilization.
Great, thank you, Karam.
Next.
On to the next slide.
It has, EBOF has multiple use cases. I mean, we can talk about it, hyper-converged infrastructure at CI, and one of the use cases is where NVIDIA has a GPU direct storage application. What does it do? They have a point on a burst buffer application, right? The data comes out from the currently from the JBOF, goes into the CPUs. CPUs use the system memory buffer and dump the data to the GPUs to process it. What EBOS can do, because it provides the higher bandwidth, higher throughput, and NVIDIA GPU direct storage IO application enables the RDMA transport. So you completely bypass the system bounce buffer completely. Data directly come from the EBOF, come from the storage to the GPUs, get process it and go back, either reside inside the storage or to the expansion shelf. And we have some performance numbers where Micron has done We are partnering with Micron and get a very good data based on these GPU direct applications. I will highly recommend to please visit our booth and get more information from there.
All right, thank you, Karam. I believe the next slide brings us into Moshe. Yeah, take it away, Moshe.
Thanks. So in Playops, we provide the solution is a storage processor, which actually provide the full storage engine API to the application side by side to conventional block device. The challenge that we aim to solve is the fact that modern SSDs, especially with NVMe, but even before, performance is very high. It's more than 3 orders of magnitude higher than hard drives, and we see that I hear an echo here. So, and we see that CPU become the bottleneck, starting for a very low number of SSDs, about 2 to 3. So CPU cannot keep up with the high performance that is available from the SSDs, and generally become the bottleneck. And the storage functionality, the storage engine inside it is a main drive for that. In order to understand it better, sometimes people ask why DRAM is much faster than SSDs, even NVMe SSDs, right? So what's the problem of the CPU to handle this? And the reason, and the answer is that in order to persist the data on block storage devices, data is going a heavy transformation to become storage friendly, let's call it, or adequate for conventional block storage. The entities in the software that are responsible for that, called storage engines, prominent examples are RocksDB, InnoDB in MySQL, WireTiger in MongoDB. So data transform from DRAM representation into storage representation, and this transformation incur high processing power for operations like Bloom filter computations, merge sort operations, binary searches over large keys, and also has a significant data amplification. By data amplification, I mean read and write amplifications. Generally, on FMS and storage in SSD industries, data write amplification is referred to the garbage collection process inside the SSDs. But actually, if you look at the overall data amplification in the system, the storage engine contribute generally much more write amplification than what is going on inside the SSD itself. Typical numbers for LSM tree, which are considered write optimized data structures, the numbers are between 20 to 40 write amplification. Read amplification numbers are sometimes even larger. B+3 data structure for small key value pairs generally produce even larger write amplifications on the hundreds. So all in all, when you look at the complete stack, you suffer both from high CPU utilization to transform the data into storage format and keep up with the high rate of the SSDs, and I/O bottlenecks due to the data amplification that is generated as a side product. Another issue that we identified from customer talk is the reliability issue. For the hard drives days, there are many RAID solutions that were adequate because of the relative low performance of hard drives. When data center migrated into SSDs, the the performance penalty that you get from enabling RAID 5 solution, either software-based or hardware-based, was significant because of especially read modify write operations that generally happen. And more significant than that, the rebuild or the degraded mode performance is a disaster. So customers cannot rely on RAID 5 or RAID 6 solutions, because in degraded mode, the server is actually useless because of the very low performance. So in PlyOps, we aim to solve those issues, both of the storage engine itself, because we provide key value native key value solution, and the way we write to the disk, and this relates also to what Matthias told before about ZNS. We write in large sequential writes, similarly to what hyperscalers are doing in their storage infrastructure. And these efficient writes and immutable writes enables much better implementation and performance of RAID 5 solution. We can go to the next slide, maybe. So this is some breakdown of IO efficiency. If you look at the initial raw data set, we have multiple sources of data and IO amplification. Internal fragmentation is something that is prevalent in data structures like as a B-tree and some hash table implementations. LSM-tree, by the way, are much better in that regard. If you look at system administrators, generally over-provision volumes to withstand future needs, and many times they are not needed. And we're talking here about local storage, even, and I'm not talking about external storage. If you look at systems that are built around local storage with virtual machines or bare metal, then many times the system administrator over-provision the volumes that they're going to use, because they don't know exactly how large the data set is going to be, which also reduce the utilization. And in order to handle the reliability issue that I mentioned before, there are various solutions to that. It's huge space. Here we depicted the simplest solution, which is RAID.
We have one more minute, Moshe.
Oh, okay. So we deploy RAID 10. So it's another impact. And okay, we can go to the next slide. I try to make it fast. So by having all the storage functionality offloaded into hardware, and we're doing this with the highly efficient data structure that we invented, which very low read and write amplifications. We enable many different implementations. One is related somewhat to what Kuram said before. By offloading all the data protection, the storage engine, and compression, encryption, all stuff into hardware, we can be matched with a DPU and have a CPU-less storage node that improves cost and performance. On the other hand, it's not depicted here, but you can look at even of today's architecture. The CPU is busy with storage stuff and network stuff, and by plugging in DPU and the PSP, power storage processor, you can offload all the other functionalities that are not core functionalities from the CPU, and let the CPU run on the application. So this is short. We can elaborate more afterward.
Well, I believe our time is actually up. So I'm not sure if we're going to actually have time for questions. Although we could have a discussion if we want. Let's see, I know that the next session doesn't start immediately. So I believe we could run over without really a problem. I know one of the things that we wanted to talk about was with regard to use cases. Let's see, Matthias, with what we've discussed so far with different approaches to architectures like PlayOps with its special processor, and with Marvell approach where they have the ability to have Ethernet bunch flash with the Ethernet controller. How do you see ZNS fitting into these architectures? Because I know ZNS can work with them.
Yeah, it's a very it's a technology that adds on to the already existing. The great technology is the both Quran presented with Ethernet, SSDs, and the fabric, and PLOPs and their solution, and exposing ZNS drives as a KV store or a conventional drive. So there's a lot of synergies, and both technologies works really well with ZNS and kind of can further kind of improve the performance that they already get from their solutions.
Definitely, I can add to that.
Sorry. Sure, Moshe, go right ahead.
I can add to that for us, the ideal drive is ZNS, actually, because we don't need the internal over provisioning. We know how to handle everything. Similarly to what hyperscalers that also control the exact way and write patterns, so don't need all the internal flows and garbage collection, etc. We are the same. So for us, ZNS is the perfect drive, and we can provide the highest value for the customer using ZNS.
Yeah, so we have already confirmed that ZNS work extremely well with this architecture, the eBuff architecture. It has its own advantages and the better utilization. So yes, there is no issues working what we see working ZNS with the fabric. And in fact, we will see more data coming out and published by Marvell on the ZNS, the fabric attacks.
So how about
comment?
Sure, go ahead.
And
with PLOPs, you can even, as I said, we expose block API and key value API. With block API, you can integrate any file system and get the benefit of ZNS with no need to any changes to the ecosystem. This is a very nice benefit.
Great.
Yeah, so Marvell controller already support the ZNS, and we have seen no issues. Yeah, you can get the full bandwidth of. And the other.
Go ahead. What kind of adoption are you seeing so far with regard to ZNS? Do you have a good feeling for that, Karam?
Adoption of ZNS?
Yeah. How many of your customers are actually implemented ZNS with their Marvell controllers?
Actually, it's in the early innings at this point, right? Customers are also adopting in terms of they are running some benchmarks and would like to see what are the performance advantages they can get and what application suit best based on their needs. So adoption is challenged to answer the percentage rate, but I can say that there is a good momentum there with what can be done with this ZNS drives.
Yeah. So, Matthias, do you have a good feeling for implementations out there in the field? I mean, you're at WD, and I'm sure you
yeah.
have a feeling about how many folks are using that.
I'll echo that there's a good momentum. I think there is a big interest from hyperscalers. Multiple hyperscalers are looking into this technology, either to go on to CNS directly, or they maybe have open channel SSD architectures when they're converting over to CNS. There's a lot of synergies here. We see it both in the hyperscalers, we see it in all flash array vendors, but most importantly, when these big customers or adopters go out, they need multiple sources. And what we also see is that there is a lot of vendors that are building ZNS drives. I am not aware of anyone not doing it at this point. So that means that there's a good market for adopters and customer and SSD vendors customers to actually get ZNS drives if it were just one vendor, it would be hard to take off, but I have a hard time mentioning anyone who's not doing a ZNS product or reference platform.
Now, how about with regard to QLC? Because ZNS has a good benefit for QLC, which is obviously the less expensive for cell flash. Do you see, are they particularly oriented toward QLC, or do you have a feeling for that?
There's both use cases for TLC and QLC. The great benefit with ZNS is that we get this 3 to 4 to 5x write amp reduction. So suddenly we can use QLC in environments where we previously used TLC. But we have, there's ask for both. So TLC is very interesting for people that does databases, high IO workloads, and QLC is really interesting for medium-sized workloads and capacity, where performance is less important. So I see a lot of ask for both of them, both for, I don't see it as only a QLC. I see it as kind of the even for both types.
Great. Well, we're going to have to wrap up the panel here, but I thank you very much for Matthias coming to us from Denmark, for Moshe from Israel, from Karam coming from San Jose, and I'm actually up in Oregon right now. So 4 parts of the world coming to you. I hope you'll all enjoy the rest of the conference, and thank you very much for joining us on this panel.
Thank you.
Thank you.
Thank you. Thank you.